In this lecture, we are going to talk about how to communicate science to others and how to recognize when science is being communicated to us and then evaluate it to see if it's actually reasonable. So, scientific argumentation, how that's structured, and if it is good or not, goes way beyond just researchers giving their findings to other researchers in like a scientific forum. Science is used to inform public policy, to create and generate public opinion about things, and also it informs our personal decision making. So, learning how to critically evaluate a scientific claim being made to us is going to just help us make better daily decisions. I recommend reading Making Sense of Science Stories. It's a great and short introduction to like how to like process the information the scientific community produces and how to do that critically. Basically, as we navigate our lives, we're going to run into different scientific arguments, even if we don't realize that that is what's happening in the moment. And it'll be our job to recognize it and then to also evaluate them to determine if that argument is strong or if that argument is very weak. In general, science is always going to present a claim or an argument or an idea and then support it with evidence and explain that connection through reasoning. So we always look for CER or claim, evidence, reason statements or paragraphs when looking at scientific information or just information in general. This goes beyond thinking about just chemistry. In general, if someone is telling me something, I would like to hear the evidence following it. And I'd like them to tell me how that evidence actually supports the thing they're telling me. And it kind of goes then everywhere. So, CER, or claim evidence reasoning, is going to have a claim that states something. It's going to state an opinion, it's going to state a result, it's going to state a conclusion, and then it's going to be followed by evidence. And this would be data or referencing a series of like results that might be published in a paper. And that evidence should support that claim that was made, that opinion or that conclusion. And then following the evidence, we want to, we should expect to see an explanation of how that evidence specifically leads to the conclusion that the claim made or to the opinion that the claim made. And so in this kind of style, science writing and science communication is kind of like bad joke telling. It's like leading with the punchline and then trying to explain the joke afterwards. And so it doesn't help to kind of like build up your argument and then kind of hit it with the conclusion. Instead, start with the conclusion, let everybody know what you're building up to instead, and then just show what supports that information. And even if it isn't clearly like all in one perfect like claim, then evidence and reasoning. In general, anything that's a scientific argument will have evidence that goes along with it. All right, so we can evaluate the strength of that evidence or how that evidence in that argument. And there's kind of three things that lead to scientific certainty. So something that's certain in science is like a scientific law. Kind of below that's theory. Somewhere in the middle, it's like if I have a hypothesis based on data, I'm fairly certain about it. And then there's also like uncertainty. Like I've observed a thing or someone else observed a thing is even worse. And so it's kind of like this scale of just like how certain are we that the evidence that we're seeing is leading to this conclusion. So we evaluate three things, as I said, the amount of evidence, the strength of evidence, and the objectivity of the evidence. And I like this scale. It helps kind of break things down and it's not like rigid in any way. But there are arguments that are made that then provide overwhelming amounts of evidence, like lots and lots, like 10,000 people participated in this trial. And now we can draw a conclusion about how many people like chocolate and how many people like vanilla. Then there's kind of like in the middle. And at the very worst, when we're looking at the amount of evidence, we would be the weakest would be if we just had one single observation without being able to replicate that observation or demonstrating that we were able to do that. The strength of the evidence then is really referring to how robust the kind of study that led to the conclusion is. And this can usually be shown in like the different ways evidence is provided or the different types of evidence. And so a well-designed experiment will have multiple ways of knowing or drawing a conclusion. It's like, here's my conclusion because I did this experiment over here. I did an entirely different experiment about a different thing that supports it too, and even another one still. And so if you have multiple lines of evidence and the studies that the way the data was gathered is well designed and there aren't obvious holes, then you have a strong evidence for the claim that's being made. What we often see is just like one single line of evidence, like one study did one thing and it produced data that then led to a conclusion. That conclusion is not based on a strong set of evidence. It is pretty mediocre because it hasn't been confirmed. It's just one group doing one line of exploration and experimentation. And then the kind of like at the very bottom, the weak one, it's like that there isn't evidence or it's unrelated or it was performed by people who weren't experts in the field, like in a classroom, things like that. Or it has giant holes in it. It's just like a badly designed study. And so the data from it isn't very strong. And then we have kind of the most, I think, vague one, and it's objectivity. And so this one, when you're evaluating it, you're really looking at who did the work and why they did the work. A study that says smoking doesn't cause lung cancer, that is paid for by the tobacco industry, is not likely to be super objective. It's being funded by an organization that wants a specific outcome. And so it would be more subjective. They're going to choose what evidence to supply to support an argument, and you can't be sure that you're getting all the information. Objectivity comes when it is something that is usually has a broad range of participants, and like if it's a study on humans and a control group, and the study is not going to use participants that are like known by the group, and they're funded by public funds. They're not going to be funded instead by a private entity trying to prove something or support their own opinion. And so looking for objectivity, we usually look at who did the study or who's providing the evidence. Why are they providing the evidence? Is this just their field of study or are they being paid to do it? And is this being attached to anything? Like is if I see as like a scientific argument and then I see immediately following it an advertisement for something that scientific argument would encourage me to buy, the objectivity then it decreases, right? It's because it's being used in the context of an advertisement. And so we kind of bring these three things together, and there isn't like an equation for it, but we use these three things to kind of decide how certain or uncertain evidence is when we're looking at a scientific claim. And we actually use pretty specific terminology, although we use terminology that are kind of common phrases, and we just mean very specific things when we use it just in like everyday conversations, it means something way more vague. So if I say that I have very high confidence in my results, I'm saying like 90%. I'm very confident. If I have low confidence, I'm in like the 20th percentile. Like I'm like, I think like 20% of my experiments were reasonable. Or like I have some real gaps and holes. And likelihood kind of follows this too. And this is, I think, the one that we see used in scientific communication, and it means something to the scientific community. But the words are different in kind of, again, conversational language. And so it's really easy to then misinterpret the information. So if we have someone who is like a climate denier and they're looking at the language and say, well, like, oh, but they say likely instead of certain. And you're like, well, yeah, that's over 66%, right? No scientist is going to say that they are 100% certain that their claim is correct. They're then no longer a scientist. That is an act of belief, right? Because we can always find a way to improve an experiment. We can always collect more evidence. So virtually certain is kind of the best you can get out of a scientist. It means that they're really, really, really sure. This is like the level of law in like scientific law or theory. Extremely likely is insanely good too. It's like, I am 95% confident that this is real. And 95% is very high. Unlikely is like bottom third. Half is really just about as likely as. And when we say exceptionally unlikely, we really mean less than a 1% chance. And so I put this up here not for you to use these in your argumentation correctly. Please use conversational English. But I think this is a nice thing to look at and be aware of when you are hearing scientific results being discussed, especially in the context of like public policy being made around them. All right. So, what we need to do when we're looking at our scientific claims is first look at the strength of the evidence, and then we need to see if the evidence actually supports the claim. So, evidence can be strong evidence, and if that evidence is unrelated to the scientific claim, then it doesn't help support it at all. And sometimes it's hard to see that distinction, especially when we don't have expertise in the area. And this is a way that people make their argument sound stronger than it is. They use a piece of evidence that is like well known or strong or kind of like accepted facts and things like that. But the connection to the claim they're making is obscured or very, very weak. And so when evaluating a claim or a scientific argument, you want to really check that connection between the claim and the evidence. And if you have expertise in the area, that's a pretty easy thing to do. You'd be like, that doesn't connect at all. Most of the time, though, when we're hearing and evaluating arguments, we are not experts. And so we need to look for other clues. And I recommend looking for the explanation of how these two things connect. A strong argument will present evidence for a claim and then explain how that evidence supports it. And if someone isn't making that connection for you, if someone isn't saying it explicitly in an argument, or they aren't explaining the link between the claim and the evidence, then it's very likely that they are trying to give evidence that doesn't actually support the claim, so that way you will believe them, and not because it's actually something that they are likely certain about. And so evaluating the quality of the explanation can be a little bit harder because we're kind of using our own kind of like cues for language or missing language in the argument. So let's walk through a couple examples. So example one, this is going to be just a statement. Older children and young adults should not be prescribed CBD to treat epilepsy. Now, that's the claim. The evidence is the National Institute of Drug Abuse has reported more negative consequences in young adults than those in alcohol that use alcohol and marijuana together. And so our evidence is talking about alcohol and marijuana being used together in young adults. But our claim is looking at prescribing CBD only as a treatment for epilepsy. These are two different things. The evidence that there are more negative life consequences for young adults that use both alcohol and marijuana is probably strong evidence, especially if it's citing a study of like thousands and thousands of people. And that would be great. That would be strong. We could say it's objective evidence. However, it has no connection to the actual claim being made. And so it isn't a strong argument. You can notice then too that what follows from that is, therefore, to prevent negative consequences, we should not prescribe CBD as part of a treatment plan. So that therefore is kind of just restating the two, like it's restating the claim, it's restating the evidence, kind of putting them together. And then it's not actually explaining it. Like, why does alcohol and marijuana together tell us that we shouldn't use CBD to treat epilepsy? Like, that's not in that last sentence, which is acting as like an explanation. And this is like a style. This is like a big red flag also sometimes, that you're reading something AI generated, and that it repeats and mushes things together without giving authentic explanations with it. It's just kind of like rehashing it, like this one in example one. So then in example two, what is another thing that we see a lot when evaluating kind of bogus claims or people who are trying to sound like they're making a scientific claim that's well supported, and it's not. Often what you'll see is someone will make a claim and then they will state evidence, and that is it. And they won't explain it at all. And it's just kind of like it's this method of trying to convince someone to be like untruthful, essentially, to by giving truths like or things that would be perceived as true by the person listening, and so giving evidence of that it's strong, like evidence that's real and like good studies, but that have nothing to do with what's really being talked about or are just within the same kind of general topic. And so people will like kind of have positive reactions to those pieces of evidence, and so that makes them more susceptible to believing the claim that is being made that is not connected. And so this is one that I like came across around the pandemic time when we were looking at things that people were doing to cure COVID. And so this example would be drinking small amounts of hydrogen peroxide can cure disease, just like all disease. And then hydrogen peroxide is a strong oxidant that causes cellular damage. So that second statement is completely true, right? Like we have lots of evidence that hydrogen peroxide does redox reactions within cells that creates cellular damage. And there's a large body of evidence for that. But that body of evidence, that piece of evidence has nothing to do with if hydrogen peroxide actually hurts viruses if you drink it, or other diseases like cancer. Disease is a really broad term, and I would be careful of broad terms also. And so like these are two things that are not going to actually be truly connected, even though they are both about hydrogen peroxide, so it's topically the same. So we're going to try to evaluate the strength of the evidence. We're also going to try to evaluate the connection between the two. Let's use an example and walk through different pieces of this evaluation process. So I have here on the right-hand side an example that is based on a study that was done back like forever ago in 1995. And so let's take the statement, the scientific claim that delta 8 THC drops before and after chemotherapy treatments can prevent nausea in pediatric cancer patients. Like that is a straightforward claim. Like if you take delta 8 THC as a kid with cancer before and after your chemo treatments, then you're not going to feel as sick, which would be a marked improvement to how the child is feeling that's going through treatment. So the evidence for this would be a study. And so I pulled out just a piece, the summary piece of the article that you can read through, and highlighted the pieces that I think are key here for evidence. That we can see that the children in the study were administered a dosage of 18 milligrams per meter squared as an edible oil. And so that's going to be basically a dose based on the child's size. It had 8 children in the study. They were between 3 and 13, and they had different types of cancer. And the total number of treatments with the delta 8 THC was 480. And from that, observations of that, they were able to draw the conclusion that vomiting was completely prevented in the cases. So you can create a treatment that prevents nausea, or at least vomiting. And they saw very few side effects, which is very exciting. So let's just break this out because that sounds great. The things that I notice are the dosage is important to know. And so the being given the exact dosage, there's the numbers, everything about this is giving you all the information. Then that kind of makes this a far more objective study and statement right off the bat. This is also being published in Life Sciences. So it'll be a publication that's well known for having a strong peer review process. We could look at the back and we could see how it was funded, and most likely it's going to be an NIH, like a National Institute of Health grant, and so not tied to a like commercial entity. And I did put that on here. I apologize. Now let's look at the amount of evidence and the strength of the evidence. And so looking at the strength, this has one line of evidence, it looks like. It looks like a well-designed study in that, They took quite a bit of data. They looked at this over 8 months, and they have a large body of information to compare this to. They could just take the entire population of pediatric patients going through chemotherapy, and observations from that to compare it to. It looks like they have also put in replicable amounts of time, so this study could be repeated. And so the strength of the evidence in terms of like how well designed it is, it looks pretty good from what I can tell. And they also are only doing this one single study. And so that sounds like there's a single line of evidence, but it's well designed. And if we dig into the details, we'll either become more or less convinced of how great the design of the experiment is. And that would be kind of digging deeper and go look at their methodology. All right, now let's look at the amount of evidence on this one. So this is 8 kids. 8 children were studied, and that is it. Now, granted, they were studied over a long period of time. They got 480 trials at least, which is a large number. It is still just in the hundreds. It's not thousands. And so the amount of evidence here is actually pretty small. This, to me, when I see that it was only 8 people that were studied, and that they drew the conclusion that it's completely prevented, that is a little bit of a red flag that the amount of evidence here isn't enough to make that statement. And so while it's more than one observation for sure, it's definitely not lots of evidence. And so if someone was making the claim that a pediatric patient should use delta H drops, and they were just using this as evidence, and this article, the research within it was their only evidence, I would argue that it is definitely helpful to making the decision, but it is not a particularly strong argument if this is the only piece of evidence that is supplied for the claim. But you could improve that strength of evidence by then finding other studies that supported it, and if you had a large body of research done by different types of research groups or different scientists that were all coming to the same conclusion, that would be lots of evidence instead of little evidence. All right. Let's break this down into its pieces too. If we wanted to actually turn the article that we saw as evidence and the claim that we're making into a statement that would be easy for someone to read and see it as a scientific argument and believe our scientific argument, we would try to use claim evidence reasoning or something similar to do that. We would lead with our idea. We would then immediately supply evidence, and then we would explain it. So using this same example, we could write a statement that had a claim that children undergoing chemotherapy should be prescribed delta H, like oil drops, THC drops. The evidence, we could say in a study by the author Abrahamov et al., published in Life Sciences in 1995, nausea was prevented in children that were receiving this dosage of delta H THC drops. And then our reasoning would be that the delta H THC prevented nausea. And we can also make the statement that if it prevents nausea and delta 8 has lower psychotropic effects than delta 9, it could be an important thing to use in a patient's treatment that is a pediatric patient, because it'll have, with fewer psychotropic effects, it'll have less harmful side effects on the child, while also reducing the effects of chemotherapy. So if I was going to put this all together into a statement that I was writing for homework or for anything like a blog post, I'd say children undergoing chemotherapy should be prescribed delta H THC oral drops. A dosage of 18 milligrams per meter squared of delta H THC has been shown to prevent nausea in pediatric patients, and therefore it should be used to reduce the nausea side effect from chemotherapy. And so we took the claim, the evidence reasoning, we kind of shortened it. A lot of times the reasoning is kind of repeating some of the evidence as it explains it, and you can kind of combine those into one, as we did here.